We starting? All right, we're starting. Hello, everyone. It's May 24th. What a day! So this morning the furniture finally arrived. Took them like what 20? No, 6. And the move was on the 6th, so it's 18 days, right? It took 18 days. So today finally arrived. My God, the amount of boxes that's piled up in the living room was ridiculous. And I think the moving company did a good job. I mean, the ones that helped us unpack did pretty well, compared to the guys that moved for us. Actually, when we set up the platform for weightlifting, it was just eyeballing. I was just eyeballing everything and didn't know if the sofa would fit. And fortunately, it did. It fit with like I think maybe 3 inches, 3 inches of room to give. So it was perfect. And then, unboxing and everything, I was doing everything as fast as I can because I don't want to have everything piled up on top of the platform because I need to lift tomorrow morning. So that one took a long time to unpack. So now we are at a pretty good place. Um, Everything looks fine. And the only new problem that we have, there's always going to be a problem, is the AC stops working. And I don't think it's the AC problem. I think it's the outlet problem. We don't have any electricity on the outlet. So we'll have to submit a maintenance request, I guess, just to see how things go. All right, so let's get to today's challenge. I saw it already. They're freaking crazy. Look at this. Look at this. I think this one I probably haven't. I've done it before. Ooh, look at that. Oh my, it was tough. Holy guacamole. It's like what, the third difficult one in a week, right? Alright, just calm down. And, we don't have much time, right? It's already 11 p.m. So what we're gonna do is we will give it a shot. If we can't do it, we have no hints. Wow. Alright, well, when was the last time I do it? Last year. March. Okay. You're given a 2D array of integers where envelopes I equals width and height. One envelope can fit into another if and only if both the width and height of one envelope are greater than the other envelope's width and height. Return the maximum number of envelopes you can Russian doll. You cannot rotate an envelope. So, okay, so we have something similar, right? We have something similar. And the length is, Jesus, 10 to the 5th. Okay, let me think. Let me think. We have faced similar problem 2 times already. The first time is given a dot and it's say how many it's inside. Oh, that's slightly different. The second is given a flower and see given a time and how many are blooming. What's the blooming solution? A number that's open and a number that's closed. I'm going to do a minus the 2. This is different. This is envelope, right? Okay, so the first one we have 5 and 4. So we can put, right, so width and height. So height is 4, width is 5, right? 5 and 4. Next one is 6 and 4. So that, oh, it holds 6 and 4. And then 6 and 7, 6 and 7. And then 2 and 3. So maximum is all of them. Hold on. 2, 3, 5, 4 are greater than. So equal doesn't work. Has to be greater than. So basically, this problem is if you give a coordinates, a Cartesian coordinates, right? And then when these are just points. So the question is asking, if I give you all these points, give it this point, give you this point, give you this point, and give you this point, 2 and 3. Tell me how many rectangles, right, can cover because it has to be, we can sort. Okay, what will we do after we're sorting it? We're trying to see how many, right? How many an envelope can hold. So how many it's contained within. That's the problem, right? So if I given any point, we want to see how many points are contained within. That is not correct. Okay, that is not correct. It's going to be dp, right? For sure it's going to be dp. So what I need is that I give them a point, and then I need to find out among the points that's smaller, that contains within me, right? That contains within me. If I know the total number of envelopes, Russian dolls, for each point, and let's say we know that. Now to give it a new one, then I just need to find everyone that's smaller than me, everyone that's contained within me, right? I'm going to find everyone that's contained within me, and then we find the maximum among them. But the process of finding the ones contained within me, oh, and I have a value. I mean, if I sort, okay, if I have to say sort based on width, okay, so then I give them something that I know to my left, they're all smaller than me on the width. Mm-hmm. You can actually do like a dictionary, right? The width and associate height when I sort them. The width, associate height when I sort them. Okay, I have all these width, and then if I consider a certain width, and I only look at the thing that's smaller than me, so the things to my left, okay? So everyone is smaller than me, and I don't have to look at all the things that have the same, that because it doesn't work. Okay, so I'm smaller than me. All I need to find out is given my current height, right? I have a height because I'm looking at myself right now. I have a height, and then for the next smaller one, we can binary search to find out whether it's smaller than me, right? Then I want to know that one, that particular one. How many then that one contains, right? Okay. Do I look for something smaller? So I have the same width, but it's something smaller height. We don't have to. So we want to find the largest height that's smaller than current me. Okay, so we got that. Then what? Do we go something smaller? Well, we don't go something smaller, because if we go something smaller, that's just smaller on the size. Well, but it might happen that it's smaller on the width but higher on the height. Oh, might contain more. Might contain more. So you're saying we have to go, it's 10 to the 5th, right? O(n) log n is the most we can do. The one that you're describing is O(n squared log n, which doesn't really work because you cannot check one by one. Well, I mean, we don't check one by one. So each one I check, right? And then I go to the next one, I check. And it's guaranteed with the same width, okay? And if you have a smaller height, you definitely have smaller. So for each one, I'll check. Each one I check. Whenever it's smaller than what we already have, then we don't check anymore because it's always going to be smaller. I think we can try. Oh yeah, finally I have. Oh shoot. That's very tragic. I think I just... I got it wrong. Oh my god. A reset hard. Okay. Should be 5. I have an idea. Alright, so the idea is we're gonna have a DP. It's going to be a dictionary. And then we're gonna say for width and height in envelopes. No. Okay, we are going to use as much vim as possible. So okay, DP. Oh, hold on. So what we want to do is hold on, this one. This shall be a default dict. So we go here. Okay, so should be this default dict list, right? And then we say dpw, no, w dot append h, right? Once we're done, I'm going to say for heights in dp dot values dot sort. Okay. Oh, we also need from bisect import bisect left. Okay, so well now. So we get that, and then we're gonna say width equals sorted dp. Okay, so I have this. Now, what we need to do is for each one, so we need to calculate everything. Oh, this is gonna still. Oh, that's on. Okay, that's on. So what we're gonna do is we're gonna go through every single one, right? For each one. Well, that's not DP. That's not yeah, it's not DP. That's just heights weight. So let's go. We can actually try. Hold on. I don't think. No. What do you say? Height weights. HW. HW. Okay. And then we need DP now, right? DP we're gonna store what? So store for each weight and heights. So how much is weight and heights? 10 to the 5th. No, so for this weight and this height, tuple. Right. So yeah, DP is gonna be like this. And then for width in WS, right? Actually what I want. What do I want? What do I want? I want I enumerate. All right, and then we say, oh, hold on. We can use IJ. Let me think again. Weight, right? And then no. Okay, we say if I is equal to 0, then dp weight, width, and height shall equal to 1, because I only have one. Else, so the smallest row, the smallest width, and for all the heights, right? They're all gonna be 1. Now, if I is larger, then what we can do is we go through I one and one smaller, right? And then we binary search and we check that one, right? And we basically say, that can be default dict as well. I just realized. Let's do default dict. It can be default dict lambda 1. Okay, so everybody is 1. So in that case, if I is larger than 0, okay, and then, okay, now we can call. Then we're just gonna go one smaller, right? Then we're just gonna go for, actually, if you're gonna do it that way, we can say for I in range from I to -1, right? So we are going actually from I -1. It's actually I -1, right? The one above you. Okay, for each I, we will get the index, right? How do we get the index? Well, we get the index by using bisect. So when you say index equal to bisect left HW WS II, right? That's that. And this one should be current height. Okay, so the current height, we go to one above me and I find where it is, and it's bisect left, so it's equal here, right? So now what we are looking for is this, the insert right in front of me. Okay, so it should be this one. -1, right? This one -1, unless index is 0. If index is 0, that means you're the smallest, right? If index is 0, then you don't do anything. And what we say is if it's not larger, yeah, because the ideal is at this height, right? If you cannot get with this width, when you get width smaller, you're always going to be smaller. Oh, hold on, no. Hold on. We're saying kernel width and height, right? And then the next one will be smaller width, and we'll go to smaller height. And it could be the other one has a higher height. Oh. I can see a scenario when your width gets small, but your height becomes really high. So when you have a high width, you don't get anything. And you have to wait until you get a low width for you to get something. But are we just looking for the maximum, right? We're looking for the maximum from, no, hold on. The max from this to this. Well, it's always going to be increasing because each one has the same width but different height, but increasing height. So no, that's not a problem. The problem is I want to find at different positions in each row what is the maximum value. That's what I want to find. That's what I want to find out. Otherwise, as I gets bigger, this is 3 levels. It's like O(n) squared. I guess this is why I timed out last time. And I cannot just jump out because at that stage, I think I'm in the wrong mindset. And it doesn't time out. Oh, even if timeout, let's just make sure that it's correct, and then we'll handle timeout when it happens. Okay, so this one we say if index is larger than 0, because if index is 0, we don't really do anything. So if index is larger than 0, then say dp width and height, dp width and height equals maximum dp width and height. 1 plus dp with okay, what's the height? Height is going to be index minus 1, right? Index minus 1, so HW WSII, right? This is the height. When I say index minus 1. This is if index larger than 0, then we should send them blah 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 blah, do all of them. Now we have to. Unless, no, there's no unless. Because I have a very flat, right, very low but wide, a very fat envelope, and I can have a very tall envelope. So the tall one has a smaller width, right? Because we're going with the width. So we will go to the fat one first, which will give us very few envelope. And then we have to go to the smaller, so I have to go one by one, and that's 3 levels, my god. And then once we're done, we're gonna return. What do we return? So return dp. Oh, it's actually gonna be maximum of dp.values. Because that's what we want, right? Just all the values. Empty sequence. So this is no good. Should be b, which is equal to this. And then say if I is equal to 0. Now we just go with dp of h plus 1. Yeah. This is going to timeout. So we get a timeout, and then we will try to see the accepted solution. Well, I mean, the good part is we directly go for timeout. We get much faster reaching there, but yeah, I'm not gonna spend too much time on this. So what is the trick? I have this in my mind. What is the trick? Ascending on width, but descending on height. Okay, I didn't really read the code, but that seems to be the key, ascending on width, that's what we do, and descending on height. So width go up, and if it's the same, okay, so that's the sorting result. Then what? Let's say we're at a certain one, we want to find the maximum number that's contained within this one, right? Then we look to the left. It doesn't make any sense. I don't know. And I get heights. What? And the height just going down, going down, going down, going down. Bisect on DP. Heights. So this is the smallest with the highest height. When given a height, oh, bisect. What the hell is this DP? DP equals, oh no, index equals, hold on. What the hell is this? we're putting heights. So we put the smallest, okay? And the next one coming up. This is the previous heights. Heights are increasing, okay? Heights are increasing. And then we have a new height, okay? And this new height, we'll look at previous. So it's guaranteed previously because at each width, right? Each width, the height goes down. And then I'll pick the smallest. So the smallest width, smallest height. Okay, that's fine. And the next one, right? Next one will go large to small. Okay, from large to small. Basically what we're saying is for each one, oh, I think I see where this is going. So this one can work. What we need to do is go, so we want to find the best scenario. So it's kind of greedy, right? So each step, what we want is to, find the next smallest rectangle. The next smallest rectangle. Now when you put it that way, TRE, that's fine, totally fine. Okay, so we're gonna go this, and then we're gonna do all this. And then so we have this, right? And then we're just gonna go one by one. Yeah, that's actually a stack. What we're doing is we're building a stack. We're building a stack, a monotonic stack, So the goal, right? We can actually, let's see. Say the goal is to build a stack or a non-decreasing stack. Right? Non-decreasing stack. And making sure that each new height pushed onto the stack not only has higher height but also larger width. Okay, so with that in mind, what we can do is for W in sorted HW dot HW, and we need to change this reverse to true. Right, and then we'll go one by one. Okay, one by one. slightly bigger than the next one. Yeah, the thing is just we want the new one to have lower height. We want height to grow as slow as possible. So height grows very, very slow, right? Very, very slow. Because if we have a smaller width with a higher height and a slightly larger width with a smaller height, and the larger that's these two kind of cancels out. So the prospect is to have lower height has a um, better chance of enveloping more, right? Yeah. So basically, we can just say actually we can do this in we can enumerate this. So if I equal to 0, stack append have w, so hw w what we want to do is to go through every single one, right? We go through every single one and then we replace the value on the stack. If I am smaller, have a smaller height, because it's a larger width but with a smaller height. But why does this work? I have a larger width, but I have a smaller height. Hold on. I don't understand. Why can we replace? I know this height is larger than index. No, it's not larger than index. It's hold on. But it's larger than index minus 1, so I replace that with h. But why can I do that? Because it could be. Alright, I understand. Longest increasing subsequence. Oh. Oh, my ability to think just drops. Okay, I think I know. So I'll code it differently. I see. Hmm. Then how do the longest increase in subsequence? Why didn't it work? Maybe I can solve it myself. Hold on, let me think. I want to see if I can be added to the longest subsequence. So I suppose I have a longest subsequence up to now. Okay, and I binary search it. If I'm the largest, then I push it in. If I am not the largest, then why do I replace? It's like I know how to solve it. Binary index tree. Jesus. What's the idea behind it? You see, I see this, but I still don't know why this one works. I don't know why this one I can replace. This is something I don't understand. How can I replace a value? What if the current n is very small? If the current n is very small, then I replace the start. What the heck? I have 10, right? And now when 9 replace 10, and 2 will replace 9, and then we'll go 5, and 3 will replace 5, then we go 7, 101, and 18 will replace 101. One will replace 3, right? Two will replace this. I don't understand. I don't know what's gonna happen. Yeah, you see, 1 comes to the front. How is that right? Come on. So we already found an increasing sequence, right? And now we find something that's smaller, bigger than this, but smaller than this. Then we simply replace it. Okay, I will simply replace it. So what's the purpose of replacing it? Because by replacing it, we make sure at this position we have the lowest possible value. Okay, at this position we have the lowest possible value, but it doesn't hurt. So every time we push in, we encounter a new one. It's either smaller than what we have established already, or if it's bigger. If it's bigger, we definitely push it at the end. If it's smaller, then we can choose to ignore. But if it's smaller than the last one, we shall replace the last one. Oh, I think I know. We try to make every position as small as possible. Okay, that's the goal. To make each position as small as possible. And as I go through from left to right, if we find something that's smaller that can put into the previous position, we just put it there. But by putting it there, it doesn't really change anything, right? Because in the initial position, this value, let's say it's a 2. Now you put a 1 inside. It doesn't matter, right? We can just assume 2 is still there. But by putting a 1 in there, we're increasing the chance that the next one can be taken out. Yeah, let's imagine a scenario. You have 1, 1, 5, 10. Okay, that's what you have, 1, 5, 10. And now thing, right? So by changing 5 with 2, become 1, 2, 10. But in reality, we still have 1, 5, 10. But it just says, okay, if we put 2 in there, there's a higher chance we're going to place the 10 compared to 5. So now we have a 3 comes in, right? So initially I have 1, 5, 10. If we have 3, still at 3, length is still 3. But my chance of adding a new one is much higher. I see. I see. In this case, yep. 354. Okay, this is a tough one. Tuition is to sort envelopes with width ascending and height descending. Now the problem is converted to take one height per width, right? What is the longest increasing subsequence of these heights, right? No, actually no, I'm going to say take one height per width, right? Take one height per width. What is the longest increasing height arrangement we can find? And this is equivalent to finding the longest increasing subsequence in the inverse and the reverse sorted, and the descending sorted heights. Per each width. Oh. The algo to find the longest increasing subsequence is very smart. We maintain a monotonic stack. Each time a monotonic increasing stack, right? Monotonic increasing. Each time a new height is larger than the largest in the stack, we append it for sure. Otherwise, we find the index of the height in the stack that is the smallest, that is larger than the current height, and we'll replace that value with the current height. Now what we're doing is to ensure that the monotonic stack increase as slowly as possible. Now this is not to say that our final solution will include the newly added smaller heights, but the total number of heights in the stack is correct. All we're doing is to provide a better chance, right? A better chance for future extension while not modifying the number of values on the stack previous at the moment. So that is the smart part. And this one will run O and log in. Okay, so first of all we need to sort. So I say envelopes sort lambda tuple return top 0, which is increasing. Top 1, which is supposed to be a decreasing. Okay, and and then we have a stack. And just a -1. And then we say for height in envelopes, and then we say index equals to bisect left, right, doesn't really matter. Stack height. Say if index is equal to len stack, and stack dot append h, means h currently is the biggest. Else if it already exists. So stack index, right, is equal to current height, is larger than current height, right? Then we'll replace it and say stack index equal to current height. Right, we'll try to make them smaller so to increase the chance. Okay, so is that it? Key. Okay, that'll be it. What a struggle. Oh, this is the same method, right? The difference is dramatic. '87, '84, so we added test cases. Otherwise, it's the same. Yeah, otherwise it's the same. Alright, that would be it. Wow, what a struggle. But the good thing is kind of, just review, right? We review the algorithm, how to solve longest increasing subsequence. It's a pretty, I guess it's a pretty standard algorithm. That will be it. I'll see you guys tomorrow. Adios.